The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
So we're getting close. We're in the last unit. We're doing kinetics, and we're going to talk about reaction mechanisms today. So we had a little bit of an introduction to that already last lecture, setting up to do this. So today we're going to run through and talk about how you come up with reaction mechanisms, how you evaluate a proposed mechanism in terms of the experimental data. So this is again in chapter 13. All right, so suppose you have a particular reaction. You know that 2NO gas plus O2 gas go to 2NO2 gas. And someone has come up with some experimental data for you. And they figured out that the rate law for this reaction, there's an observed rate constant, so K observed. And in terms of the NO concentration, it's second order. And in terms of O2, it's first order. And so now you can come up with a reaction mechanism that fits that experimental data. And as I mentioned last time, you never know for sure that your reaction mechanism is correct. All you can do is be consistent with the data. You can prove reaction mechanisms wrong. You can come up with a mechanism and show that that can't possibly be the mechanism given the experimental data. So you can prove things wrong, but you can never be sure that you have it right. So the best you can do is consistent, but you can prove a lot of things wrong. And if you have a lot of mechanisms and you prove a lot of them wrong and there's only one that seems to hold, then there's a good chance that's probably correct. But you never know 100% because someone might do another experiment and discover something else. But in the problem set, you'll be saying, yes, this mechanism is consistent, or you'll be writing a consistent mechanism, or you'll be saying that mechanism can't possibly be true. All right, so let's look at that. First, let's just consider what the overall order of this reaction is. So what is the overall order if this is the rate law? 3. So I'm just running through these. We'll practice some of these because these are good, couple point questions on the final. And so you don't want to miss these easy points. All right, so if the overall mechanism is 3, so the overall order is 3 things coming together at once to react, is it likely that it's one step? No, it's not. What is it called if you have 3 things coming together in terms of molecularity? Right. Termolecular. And those are rare, as we talked about last time. So as I said, if you're getting together 3 people, it's usually not true that they all arrive sort of ready to go at the same exact moment. Usually one person is late, if not more. So getting 3 things to react together at the same time is challenging, and so those are rare. So this probably has more than one step. So then we have to try to divide up this reaction into steps and come up with a mechanism, a two-step mechanism. We'll try for this. Yeah, let me leave that up. All right, so let's draw a potential mechanism on the board. Okay. And then we'll try to figure out for that mechanism what the rate law would be if that was the correct mechanism, and see if it's consistent with the experimental data. So again, what was the experimental rate law is K observed. So that's the observed rate constant. Second order in NO. And first order in O2. So we can write the reaction in 2 steps. And each step is an elementary reaction, so it occurs exactly as written. So in the first step, we'll have 2 NOs coming together. And the forward rate constant will be K1. and the reverse rate constant will be K minus 1, and it'll be forming an intermediate N2O2. In the second step of the reaction, we'll have oxygen come in and interact with the intermediate N2O2 and form with a rate constant K2 two NO2s. And that will give us our overall reaction. So now we need to write rate laws for each step. And since each step is an elementary reaction, we can write the rate law using the stoichiometry of that step as written. So the rate of the forward reaction, the rate law for the forward reaction would be what? What do I put first? K1. And then? NO squared. What about the rate for the reverse reaction? K minus 1 times what? N2O2. Okay, so let's look at each of these. For the forward direction, what is the order? The overall order is 2. And so in terms of molecularity, what is it? Bimolecular. Bimolecular. Okay, for the reverse reaction, the order is what? 1. And what is that called? Unimolecular. Okay, so let's look at step 2. So the rate for step 2 is what? K2 times, so it would be O2 and N2O2, the concentration of each. So again, we can write them exactly as written. So now we consider the rate of N2O2 formation. So the overall rate of NO2 formation from these two steps. And we can just use the second step where NO2 is being formed. And so we can write this is equal to that rate law times 2. So let me rewrite the rate law. And the 2 comes from the fact that 2 NO2s are being formed. So because 2 NO2s are being formed, this concentration is increasing at a different rate than the concentrations of these are decreasing. The book is inconsistent with whether it puts a 2 all the time. So I'm not going to take off if people forget to put the 2 in this, because the book should be more consistent with that. But that's where, if you do see a 2, it will mean that you're forming 2 of the products in the reaction. All right, so now we've written a rate. We're not equal to our experimental rate here because there's an intermediate. So this is an intermediate. And an intermediate cannot appear in the overall rate law for something, so you're going to be spending a lot of time getting rid of intermediates. So let's now leave this here and try to get rid of our intermediate. So, trouble with papers today. So now let's solve for the intermediate. And we want to solve for this intermediate in terms of things that are not intermediates. So we want to solve for it in terms of reactants or products or rate constants. So we need to consider then how NO is being, and how this intermediate N2O2 is being formed, and how this intermediate is being consumed or decomposed. So we want to figure out the net formation of the intermediate. And the net formation of the intermediate is going to equal the rate at which it's formed. So it's being formed over here in the forward direction of the first step. So we'll write that down. So we consider how it's being formed. It's being formed with the rate K1 times the concentration of NO squared. So that's just the rate law for the forward direction of the first step. It's also being decomposed in the first step in the reverse direction. So it's being decomposed with the rate of K minus 1 times the concentration of the intermediate. So that's just our rate law for this reverse step of the first reaction. And it's also being consumed. It's also being consumed in the second step with a rate law of K2 times the concentration of the intermediate times the concentration of O2. So that's just the rate law that we wrote for this second step. So it's being formed, decomposed, and consumed. So the net formation equals the rate at which it's formed minus the rate at which it decomposes minus the rate at which it gets consumed. And now we can use something called the steady state approximation. So in the steady state approximation, all it's saying is things are in a steady state. So that means that the net formation of this intermediate is equal to 0. Or if it's in a steady state, that the rate at which it's being formed is going to be equal to the rate at which it's being consumed, either by the reverse step 1 or step 2. So that this rate is equal to this rate. That means it's steady. So it's in the steady state. The net formation is 0. The rate at which it's being formed equals the two rates at which it's being consumed or decomposed. The rate at which it's decaying are equal to each other. That's the steady state approximation. And it's a very good approximation. And so you can use this for all of the mechanisms that you'll be writing. So that allows us to set it equal to 0. Or we can rearrange these terms so that these two are on one side and the rate at which it's formed is on the other side. So let's do that. And I'm going to take these two and put them together and also pull out the term for the concentration of the intermediate, because I want to solve for that term. So I'm going to try to pull it out and solve for it. So if we rearrange this, then we get that the concentration of our intermediate, you pull it out from those terms, so that leaves K minus 1 plus the other term, K2 times O2. So now I've just pulled this out from these two, and I've moved these to the same side of the equation. And so that's going to be equal to K1 times NO squared. So this is the rate at which you're decaying your intermediate, and this is the rate at which you're forming that intermediate. Now I can continue to solve for this. So the concentration of the intermediate is going to be equal to K1 NO squared over K minus 1 plus K2 times the concentration of O2. So here is what the intermediate then is equal to. And now I can take this term and go plug it back in. All right, so we can take the concentration and plug it back into here. So that whole term that we just came up with, and we'll put it back into that equation. So then if we substitute, we get the rate of NO2 formation is going to be equal to 2 rate constant K1, rate constant K2, times NO squared times the concentration of O2 over K minus 1 plus K2 times the concentration of O2. But that's not consistent. We have NO squared and 2 O2 terms, whereas in our observed experimental law, there's only one term for O2. So that's not consistent. So something is wrong. So this is not consistent. So there must be fast and slow steps. If there are fast and slow steps, then we can simplify this equation and make it like the experimental equation. So now we can go over here and think about what would happen if step 1 was fast. So it's a fast and it's a reversible step. It's already written that it's a reversible step. So it is reversible. And step 2 might be slow. So now we can consider if we have a fast first step and a slow second step, what that would do to this equation, and whether we could then rearrange this equation such that it would be equal to our experimental rate law. So when we say something is slow, we're going to introduce a new term, and that the slowest step in a reaction mechanism is called the rate determining step. And for a rate determining step, you can assume that that step is governing the overall rate of the reaction. It's slow enough that the rates of the other reactions don't really matter. And that's what rate determining means. And let me just give you an example of a rate determining step. So after today's lecture, you will be able to do all of the problems on problem set 10. This is your last problem set in 511-1. And so it would be really great when that problem set is finished and turned in. And so all through the rest of this lecture, you're thinking about, I can go out right after class and finish that problem set. So you're very excited. And by the time it gets close to the end, you see the end of the handout coming up, your books are sort of packed, you're ready to go. And then the minute it's finished, you're out the door. And you're going to some place where you can sit down and finish problem set 10. So you're moving really fast. You might even be running. You may be even jumping over people in the infinite corridor to get to the library as fast as you can. So you get to the library and you look for a table, but everyone else from 511-1 somehow is already there, and all the tables are filled. And you go to the first floor and the second floor and the third, you go to the basement and the stacks. Every table is finished, filled up with people doing problem set 10. So then you have to leave the library. You think, building 2, lots of small classrooms. They can't all be in use. So you run over to building 2. But all those classrooms are filled with 511-1 students doing problem set 10. And so eventually you get to building 4 and you find a free classroom. The second you find that free classroom, your books are out of your bag, they're out, your calculator, your correct kind of approved calculator is right there, and you are ready to go. So it takes you maybe 2 seconds to get out of 10250, and it takes you maybe 2 seconds to pull out all your books to be ready to go. But it takes you a half an hour to find the table to do that problem set. So overall, half an hour plus 4 seconds is a half an hour. So that was the rate determining step in finishing problem set 10, was finding that table. So what you can do for these as well, if we say there's a slow step, you can assume that that's rate determining. And you don't have to worry about how fast those other steps are. It just depends on the rate of the slow step. That is governing the overall rate at which the reaction or the process happens. So that's rate determining step. So we can use that now. And we can use that and go back and simplify the expression that we solved for the intermediate. So here we were solving for this expression, and we weren't considering anything about fast and slow steps at this point. And so this is the equation that you would get if there were no fast and slow steps. And then we plugged it into this and found that it wasn't consistent. So now let's take a step back and go back here and think about what this expression would be if the first step was fast and the second step was slow. So here again, I've just put it up on the screen, what we had on the board. So we have this first step is fast and reversible, and the second step is slow. So really what we're talking about here is we're comparing rates for the decomposition of the intermediate, so that's the reverse direction of step 1, with the rate for the consumption of the intermediate. So which of these is faster? Well, decomposition is faster because this is a fast step, and the consumption in step 2 is slow. So what does that mean? Well, if we write it down, then if the rate of the decomposition, this rate, the rate of the reverse reaction, is faster, then this K minus 1 is a bigger number than K2. The rate of consumption here is slow. So we're going to consider the relative size of these numbers and how they fit in this term, and you can drop things out by assuming that one thing is a lot bigger than the other thing. So if we do this, then we're saying, again, this is the same thing that was on the last slide, that the rate of the decomposition is faster than the rate of consumption, i.e. step 2 is slow, step 1 is fast. What you're saying is that K minus 1 is a bigger number. That rate constant is a bigger value than the K2 term. And in the bottom of the equation here, in the bottom of this equation for the intermediate, we have a term K minus 1, and we have the term K2 times the concentration of O2. And now if you're saying this about the different rates of this reaction, if you're saying this is fast and that's slow, this is a big number, that's a small number, if you have on the bottom here a really big number plus a much smaller number in comparison, this smaller number isn't adding much to the bigger number. And we can just cancel that term out. It's not insignificant, it's just, we can just say, it's so much smaller than the other, we're not going to worry about it, and we're going to get rid of it. So now our expression would look like this, that the concentration of the intermediate is K1 times NO squared over K minus 1. So we can rearrange this and think about, does this look familiar to any of you in terms of what we've seen before? So we can rearrange it to look like this. And what is this term? What is this all equal to? K, the equilibrium constant. It's equal to K1. So this is just an equilibrium expression. And if you go back and look over here, you see that if you're going to write the equilibrium expression for step 1, products over reactants, that's what you would get. And also, we saw last time that you can express equilibrium constants in terms of rate constants, and the equilibrium constant for a reaction is going to be equal to the rate constant for the forward reaction over the rate constant for the reverse reaction, and at equilibrium, those rates are equal to each other. So this is just an equilibrium expression. So when we assumed that step 2 was slow and step 1 was fast, we can now solve for the intermediate in terms of an equilibrium expression. So let's consider why this is true. Okay, so when you have a fast first step followed by the slow step, the first step is pretty much in equilibrium. The first reversible step is in equilibrium. And that, you can kind of think about it in terms of this diagram. So here you have reactants going to intermediates, and this is fast and reversible. Then the second step, the consumption of the intermediate is slow, going to products. So if this is really pretty slow, and not much of the intermediate is being siphoned off to product, more of it in fast equilibrium is going back and forth with the reactant, then that creates a sort of an equilibrium expression. It's not perfect. Some of it is being siphoned off, but more or less, you can consider this in equilibrium. So again, if you have a fast reversible step followed by a slow step, you can assume equilibrium conditions. And that's going to make your life easier in terms of solving these expressions, because you can go right to writing an equilibrium expression then for your intermediate. So now we can go back and substitute. So we have this term now for solving for our intermediate, or you can write K, rate constant K1 over K minus 1, or you can write big K, the equilibrium constant K1, and these are equal to the concentration of the intermediate. So we can put this term back in here now. This was, again, what we wrote in the very beginning for the formation of NO2. And we can substitute that back in, and we can have it in terms of the rate constants or using an equilibrium constant in there. Those would be equivalent. And all of these K's in terms of the experiment are going to be grouped together as a K observed. So you usually aren't going to measure all the individual rate constants. You're just going to have some overall rate constant that you do measure, an observed rate constant. And so if you write then either of these in that form where all your K's just get grouped into K observed, then you see that that is consistent with the experimental data. So that mechanism works. A mechanism works that has two steps. The first step being fast and reversible, and the second step being slow. So we don't know for sure that that is the mechanism, but it is consistent with the experimental data. So let's look at another example now. So we're going to look at three different examples. So here there's a proposed mechanism that's very similar to the one that we just looked at. So now we're going to try to do this problem in a more efficient way than we did last time, which is kind of work through it the way you will when you're doing problem set 10 really fast. All right, so we have a two-step mechanism, one that is fast and reversible, and a step that's slow. So the first thing you want to do is write the rate laws for each of the individual steps. So for this one, what is the rate law for the forward reaction? K1 times O3. So that's for the forward reaction. For the reverse reaction, we have K minus 1 times O2 times the concentration of this intermediate O. Okay, so let's look at the second one. And so here we have the rate K2 times the intermediate O times O3. Now the rate is going to be determined by this slow step, and we can write the equation for the formation of O2 from this last step, and we could do that whether it was a slow step or not. We did that before as well. So if we write the formation of O2, it's being formed in the last step from O and O3. So we're using this rate law, and again we have a 2 in there because, like the last example, two things are being formed. So we have two molecules of O2 being formed. So the rate of formation of O2, 2 times K2 times this intermediate times O3. So if there was no intermediate in the expression, we'd be done, but there pretty much always is going to be an intermediate in the expression, so we need to solve for that intermediate. So O is an intermediate, so you need to solve for it in terms of reactants, products, and rate constants. So again, here we have this step that we saw before. The first step is fast and reversible. The second step is slow. So you can approximate that the first step is in equilibrium. And so you can solve for the intermediate in terms of an equilibrium expression. So what is the equilibrium expression for the first step? So K would be equal to, let's just put it down here. K equals, you can write it in terms of K1 over K minus 1, products, O2, times O over reactants, O3. So that's just our equilibrium expression. We have it in terms of the rate constants and in terms of this expression for products over reactants. And now we can take this and rearrange it to solve for our intermediate. So we have this, we bring the O2 down to the other side, we bring the O3 up here, which leaves us with K1 times the concentration of ozone over K minus 1 times the concentration of oxygen gas. So that was a lot simpler than what we did over here, and so you can feel free if you have if you're told there's a slow step and a fast step, just jump right to that, solve it in terms of the equilibrium expression. It'll save you some time. You should come up with the same answer if you do it the way that we did it in the first step. And sometimes you'll have to because you won't know about fast and slow steps. So now we can take this term and substitute it back into our overall, the rate law for the formation of O2 gas. And so we had K2 times this intermediate times O3. We put this term in for our intermediate, and we get 2 times K2 times K1 ozone squared over K minus 1 times O2. And so this would be the rate law for this particular mechanism. So if that is the rate law for that mechanism, you could think about what are the orders in this, and could you experimentally go back and look and say, okay, is that consistent with the mechanism? So let's take a look at what we would predict from this. So first, we could also write this in terms of K observed, and group all the K constants together for K observed, and then that's times ozone to the 2 and O2. So if we look at this, what would we predict? If we were going to design experiments for someone to do, what would we predict to sort of prove that that is, in fact, a correct mechanism? So what is the order based on this rate law? What is the order in terms of the concentration of O3? 2. So if someone went in the lab and doubled the concentration of O3, what should they observe happen to the rate? So they should observe 4 times the rate. What is the order in terms of O2? What is it? -1, right. So if you double the concentration of O2, what should happen to the rate, keeping everything else the same? It should be half. So this is the kind of thing that can be experimentally tested, whether it's consistent. And what is the overall order then of this reaction? It would be 1. And so if you doubled both things, what should you observe happen to the rate? It should double. So you could go back and sort of test this. Okay, so let's look at one more example. So this time, we're not going to make a proposal ahead of time about fast and slow steps, but we're going to work out what the overall rate law for this is without fast and slow steps, and then go back and consider which step or any are slow. So now we're going to go through the long way and do this problem and then think about what we can learn from it in terms of we're given an experimental rate law, and once we see how this works out, we can think about whether a step is slow or not. So first we start the same way, and we're going to write the rate laws for each of the individual steps. And again, they're elementary reactions. Steps in a mechanism are elementary reactions, so we can write the rate law exactly as the equation is written. So what is the rate law for the first, for the forward direction here of step 1? First we have K1 times NO concentration times Br2 concentration, right? So that's the forward. And in the reverse, we have rate constant K minus 1 times NOBr2. For step 2, we have rate constant K2 times, right, times NO. There you go. So you know how to do these. So we have that. Now we can write, we're going to be looking for the overall formation of NOBr. And so we can write this just using the last step. So we can use that rate law, rate expression for that last step. So the formation of this, and we're putting a 2 in because, once again, there are 2 of these being formed in that last step. So again, we could just use the rate expression for the last step, and there's a 2 in there because 2 are being formed. So that's the rate of formation of NOBr. Now we have an intermediate. This is being formed, and it's being consumed, so we need to solve for the intermediate. There can't be any intermediates in our overall expression, so we need to get rid of that. So it's intermediate, and we need to solve for it. Now, we can't go and just use the equilibrium expression for the top because we don't know anything about fast and slow steps. We don't know that that's going to be a good assumption. So let's just write it out the long way and then come back and consider whether that's consistent with the experiment or we have to do some modifications. So we're going to solve for this in terms of reactants and products and Ks. So now we want to consider the net formation or the change in the concentration of this intermediate. So the intermediate is being formed in the first step. So we can write down the rate expression for how it's formed, which is just this, K1 times NO times Br2. So this is how it's being formed. It's being consumed, or it's being, decaying in the second step, in the backward step, so we can put that in. So we have a minus sign here because it's going away by the rate expression of K minus 1 times the concentration of the intermediate. And it's also being consumed in the second step, so it's being used up in that second step. So we'll put that term in here. So that's minus K2 times the concentration of the intermediate times NO. So it's being formed in one step, and it's being consumed in 2 different steps. Now we can use the steady state approximation, which says that the overall net change is 0. So we can set this term equal to 0. And it's the steady state approximation. That's the same as saying that the rate at which an intermediate is formed is equal to the rate at which the intermediate goes away. So we can rearrange these terms, bring these on one side of the equation, and have this one on the other. So rearranging then, we moved these onto one side, and the formation to the other side. Now we can pull out the term for our intermediate. So take it out here, that leaves K minus 1. Take it out here, that leaves K2 and NO. And again, this is the rate at which it's being formed. And now we can solve for the intermediate. So when we solve for the intermediate, we take this term and divide it by that term, and we get this expression. So that's solving for the intermediate. The next step is to take that intermediate and plug it back into the initial equation that we had, the formation of NOBr, and that was 2 times K2 times the intermediate concentration times NO. So now we take this whole term and put it back into this term, and we get this expression here. All right, so this expression now is not consistent with this experimental rate law. So there must be fast and slow steps. So now let's consider what's going to happen if the first step is slow and the second step is fast. Again, you're considering what's happening in the bottom of this expression. You're asking, how does k minus 1 compare to this K2NO term? And so if you say that the first step is slow, then k minus 1 is small. Second step is fast. That means K2NO is a bigger term. So if this second step is fast, the rate constant for the second step is a bigger number than the rate constant for the first step. And so what you can do then is you can say, okay, that's small compared to this, so we drop out that term. So if we drop out that term, can we cancel anything else? What else can we cancel? We can cancel K2. What else? So we can cancel out one of the NOs, and that leaves us with this expression here. So there's the expression again, 2 times K1 NO BR2, and that can be written as K observed, and look at that, it is consistent with the experimental rate. So now let's just check the other way to make sure one should be right and one shouldn't be right, that we can get the answer if we go the other way around. So this is consistent with the experiment, and the overall number of this is 2. All right, so now let's look the other way around. If the first step is fast and the second step was slow, that would mean that k minus 1 would be a lot bigger than the K2 term. K minus 1 rate constant for the first step, K2 rate constant for the second step, fast bigger than this. And so then we can take this term out. Can we cancel anything else? No, you can't cancel anything else. So this is the expression. We can put that down here. We can group the k terms to k observed. And so this is not consistent with the experiment that you had before. So that way doesn't work. So you can write out the whole thing and then think about whether they're fast and slow steps. Again, you'll be asking the question, which of these terms is bigger than the other term? What's the fast step? How does k minus 1 compare to K2? You can make the simplification, and only one should be consistent. One mechanism should be consistent. This other one should be inconsistent. Okay, now you can do problem set 10.